Hello students, today we are going to discuss about gray code and their conversions. I am Santanu, Assistant Professor in Haldia Institute of Technology, Department of Information Technology. Let's discuss what is gray code. The gray code was designed by Frank Gray at Bell Laboratories in 1953. The gray code have several properties like this is an unweighted or non-weighted binary code. This is also called the cyclic code. This is also called the reflected binary code. We already discussed the reflection properties earlier, unweighted property earlier. So we are going to skip this here. Now, the main advantage of using gray code is that only one bit in the code group changes from one number to the next number. What is that means? That means let's take an example like from 7 to 8, if the code is changed, then you can see in the binary form, this is only changing one bit. The 100 is strict here, but this 0 is changing from 0 to 1. So you can see that the only single bit is changed from 0 to 1 and the remaining bits are same. This is also called the unit distance code based on this property. Now, self-reflecting code. We are already said that this is reflected, it has the reflected property. So what is self-reflecting code? Gray code, also called the self-reflecting code. Why? Let's take an example. Suppose we have the gray code representation for m bits, and to obtain the gray code representations for the next bits, that is the m plus 1 bits, we write down two m bit representation, one below the other, then the second one being the mirror image of the first one, and we then add a 0 at the beginning of every code in the first group and a 1 at the beginning of every code in the second group. I think you don't get it. Let's take an example. Here you can see that if we consider the 3-bit, then this part and this part is same. You can see that it's start from 000 and end 100, and here it's start from 100 and end 000. So you can see this is just the mirror of this part is mirrored here. And in our second point, what we say that we then add a 0 at the beginning for the first group and 1 at the second group. Here we assign the 0 for the first group and 1 for the second group, and you get a 4-bit gray code. So this is the self-reflecting property, and gray code holds that property. That's why gray code is called the self-reflecting code. Now we are going to discuss the conversion from binary to gray code. Suppose we have a gray code. Let's say we have binary code with bn-1 to b0 and gray code gn-1 to g0, which is actually denoted the n-bit gray code and binary equivalent. Here, for the gray code bit I, that is assigned as g of I, we will get that value when we perform the XOR operation with bi and bi plus 1. Let's take an example. Here, before we are going to solve the gray code conversion, let's discuss or recall the XOR operations we already know. In our truth table of XOR gate, we know that if 0 and 0 are there, we get, there have some mistakes. If there have 0, 0, it will be 0. and 0 1 then 1 and 1 0 then it is also 1 and for 1 1 it is 0. So here you can see for this binary number this 1 is going to as it is as 1 and this 1 is XORed with this 0 and the result is 1 as we know 0 1 1 and then again this 0 is going to XORed with this 1 and the result is 1 again 1 this one B3 this one is going to XORed with B2 and the result is 0 as 1 1 is 0 and again this one then again this 0 and this one going to XOR and the result will be 1. So the final gray conversion from this binary number is 1 1 1 0 1 1. This is the truth table, or you can say the whole conversion of binary to gray code from 0 to 15, that is the 4-bit representation. And this is the conversion circuit of binary to gray code. We already discussed here that what are the operation performed. That is the MSB bit is going to be as it is and then the MSB bit is going to XOR with the next bit. So here the rules is same. The first bit is going to as it is and then first bit is going to XOR with the next one and so on. So here you can see the circuit diagram is also explaining the same, as the first bit is as it is going to represent the gray code and the second bit is going to XOR with the first one and the result is going to be our second gray code and as so on. B3 we XORed with B2 and then B4 is XORed with B3 and our final gray values are here. Then we are going to discuss the gray to binary conversion. This is a little bit different from the binary to gray one. Here the rules is the MSB bit is going to be as it is and the results will be XORed with the next gray code bit. So this is the formula. You can see that the first bit is as it is, then the results is going to be XORed with the next bit. So this is an example. This is our MSB bit, which is represent the MSB bit of binary number as it is, and then this bit is going to XOR with the gray code second bit and the result will be the binary second bit, and then the result of binary second bit is going to XOR with the gray code third bit and the result will be binary third bit and so on. So the circuit diagram is as you can see. The first bit is going to be G1 to B1 as it is. As we already know, there is a formula and you can see the example. The MSB bit is as it is and then the results is going to be XORed with the second gray bit. So the results is going to be, here you can see the results is going to be the XORed with the next gray bit, and here also because the input also same to the results, that's why it is, you can say the results or the input bits both are same. So here the results with the second gray bit, here also you can see the results with the third gray bit, here you can see the results with the fourth gray bit, will give you the 4-bit binary representation of your gray code. And this is the conversion of gray code to binary code, or you can say the truth table for 4-bit gray code to binary code. Thank you.